Time to start our next exciting lecture here. Some of you folks are just tuning in, so I'd just like to say yesterday's lab was not well attended, but I did record it, and if you need to watch it, it's available. I was just playing it here. So that's yesterday's lab, and that we were covering a review for the final project in the lab, which is due in 7 days. Today, and we also covered the homework, which is due today, so you can get some of that review. So today's agenda is a little bit different since we've already done the homework and such. Today's review is centered on the final, which is due on the 17th. So you've got a homework 11 due tonight, and you've got a final, and I've got a preview for the final as promised, so you can have 2 weeks to work on it. It's multiple choice, Blackboard final, kind of a mashup of pretty much all the homeworks we've seen. We've got 100 questions. Ooh, 100 questions. Now, here's the interesting thing. Students aren't allowed on campus, so therefore you can't go to the dean's office and complain. Ha! Also, even if you did, he's not there. So the only people you can complain to are Amy, and she's just the secretary, so she'll just nod her head and smile, and that'll be it. So 100 questions, open book, open notes. You get 2 attempts. You could take the whole thing and you could print it. God, I don't know how much paper that will use, but a lot, I'm sure. But still, you could do that. And then you could, or you could go through it while you're online and just sort of note the true falseness of each one of the questions and then transcribe it sort of in your own time before you save and submit. And in this way, I guess maybe what you could do if you wanted is sort of take a stab at it honestly and just hit submit and see what you did wrong and then do it again. And that'll improve your grade for sure, because it's the highest of the 2 grades, just like always. There's no time limit except, 2 weeks. And let me think. No lateness, right? On this one, you got to do it on time. Gotta. Because why? Because, I don't know. Let me pull out my calendar and just make sure. This thing is due on the 17th. And yeah, that's the end of the semester. So I've got to submit grades and such. So you guys have to submit this on time. So it's due end of day on the 17th. Please don't wait till the end of the day to submit a 100 question homework to Blackboard, because it's almost certainly going to break, and then I'll get an email and it'll say, "Oh, professor, blah 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 blah," and the thingy, and I lost my Wi-Fi, and then I could hit submit, and nothing happened, and no, I can't hit submit anymore. And then I'll say, "What's the matter with you?" And then I'll whine. You don't want to hear me whine, so yeah, don't submit it on the last day at the last minute, because that's just terrible. Especially because it counts for a third of your grade. A third of your grade, yes, because it's the final. So got to take it seriously. I'll review it. And in fact, you should have access to it now. Are people able to see this thing? Somebody tell me they can. Shoot me a chat or pipe in with the microphone, please. Just check. Somebody check, please. It's okay. I'm waiting. Can nobody see this? Nobody can see this? Because I'm going through it, and it's really good if you can see it. Chris, are you with us? Chris?
Yes, I can see it.
You can see it. Thank you, Chris. Oh, that wasn't Chris who was talking, was it? Who was talking?
No, that was Chris.
That was Chris. Oh, all right. Oh, thank you. So then that's good. I'm glad you could see it. So then what I'll do is I'll just kind of say 100 questions is a really lot, a whole lot of questions. And so what I'm not going to do is go through every single question in detail unless you ask me to. So I'll kind of scroll through the questions slowly, and you can ask me any question you want to about the questions, or if you want me to go over a question, I will go over it. But otherwise, I'll just kind of go slow. And you've seen all this before, I think. You've seen the MOSI and the MISO and the SPI interface, and you know what the serial clock stands for. And you've seen this, right? That's a strain gauge. So you've seen that. And you've seen this before. Let's see, what else we got here? PIR sensors, I think they were like the first lab or maybe the second lab. And then let's see what else we got here. This is cool, right? Touch sensor. You know, what's up with this? What's this touch sensor about? Anybody have any ideas? No idea. How about Jacob? You got any ideas what this does?
No, I'm not sure.
All right, so you've got your A to D converter here. That's your input. You've got your touch sensor, and so you're using the human being who touches it as a ground, right? You're basically changing the voltage that's being divided in through here by adding another path to ground. And so that is something you can sense on the A to D converter. And if you think about it, you've got another touch sensor over here, which can also alter the input to the A to D converter. So in effect, if you wanted to, you could probably implement your dual tone multiple frequency dialer with a sequence of touch sensors and just kind of, there's actually a library for this, touch the different sensors and then play the different tones, which I think would be very fun. So that's a, that's that. We've seen the strain gauge, I think. And let's see what else we need to see. Motors. Yeah, we've done motors, rotor, stator. The rotor is the part that rotates. The stator is the part that doesn't rotate, hence the name. It's not too hard to remember that stuff. Then these are Hbridges, which help us to move a motor forward or backward. You never close these two switches at the same time, because if you did, then you would have a short, right? Because this is positive and that's negative, and you close these two switches and positive and negative are connected, and then that has 0 ohms with the positive voltage, which gives you infinite current, which is really bad because E equals IR, and if R is equal to 0, then it's, well, take my word for it, it just shorts everything out. It's no good. So then here's the PIR sensor. We've seen that before. We kind of know what it does. And this is what an Hbridge looks like. You can buy them in the store. I'd say in the Radio Shack, but they don't do that anymore because there is no Radio Shack. So I guess you got to go buy them elsewhere. If you ever shop for these things, you know, you can always type it into octopart. I don't know if you guys have ever tried doing anything like that, but I mean, I'll just kind of show you real quick. If you're shopping, octopart can help you to create a bill of materials from relatively inexpensive providers. So if you type in something like Hbridge, there's a bunch. There's a bunch, and then you can sort them by price, and you can do whatever you like with them. Or perhaps you would like to sort them by, I don't know, number of outputs, max current, all these different things you can use. Interface. I don't know what the interface is. I'm assuming it's, here's an I2C Hbridge. That sounds like fun. So then you can hook that straight up to your Arduino and control it on a bus. You control your Hbridge on a bus. That's good, right? Because why? Well, because maybe you got half a dozen motors and you want to control them all through like your little I2C serial port. So that'd be cool, right? Hbridges are us. You can control all your motors through I2C. That'd be good for a robotics application. So that's a nice idea. I've never tried that. Save you a bunch of pins on your Arduino. So that's a stepper motor. We've seen that before. Here's more SPI questions. And there's a famous servo. We have these in the lab, actually. They've got little gears in them. And you can see the servo part, right? There's the motor, but then the reason we know where the motor is because of the potentiometer. So the motor is geared to the potentiometer. And so when the motor turns, the potentiometer changes its resistance, and that's what enables us to know where the motor is at. So that's the pot. They call it the potentiometer pot. And I guess if you use too much power in the pot, you'll be smoking the pot. So then here's a little servo controller. Now that's just doing a pulse width modulation. And so this is acting like what the Arduino is doing, only it's just being a servo controller board. And so what it's doing is it's taking the pulse width modulation, putting it into the servo and controlling the position of the servo without a computer. No computer here. All right, it's just a 555 timer and a little diode and a couple of resistors and capacitors and some power, and bang, you're done, a servo controller. You turn the knob over here. This is a schematic representation of a potentiometer, and then the servo shaft will turn. So you don't need a computer to do that. I think we had a little discussion about pointers and dereferencing. So this would enable us to take whatever the pointer is pointing to and set the value in that memory location to 8. Let's see now what else we got here. There's a DIN that it represents a serial port for probably a PC or something similar. These have, that's a common sort of use for a male 9-pin DIN connector. There are so many different serial port connectors that are in use. There's an 8-pin DIN, which I think you can find on old Macs and Roombas. There's a 25-pin DIN, which dates from the 60s. There's just a lot of these things. It's a bit of a circus, really. So there's the Mac version of the DIN. How many pins is that? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's an 8-pin DIN. And you can kind of see what they did here is they interfaced it to the modem or the printer. This is probably on the back of a Mac Plus or something. And then this is the 25-pin DIN, and there's a connector that goes from one to the other. So you got your choices of connectors, and it's a bit of a nuisance that there are so many choices. Let's see, we've got Bodo, I don't know. We've talked a little bit about baud rates. So I guess we don't need to dwell on that. And then let's see what else we got here. What was the question? Consider the following Arduino pin map. Please do not use normally PD0 and PD1 because that's what the SPI uses. Well, I'll let you guys ponder on that. PD0, where's that? It's here. Transmit received. Is that what SPI uses? Transmit receive? Does that sound right? You tell me. Well, where are the SPI pins, folks? Remember, sort of like MOSI over here, and then MISO, right? The serial clock, the serial select. So we're on pins 10, 11, 12, and 13. What is the point of the RX and TX line then? What's that about? Why isn't SPI using that? Any ideas? Somebody want to chime in? I'm going to call on people. John Fee. John, what do you suppose that PD0 and PD1 are normally used for?
I have no idea, Professor.
Well, that's for
Communication.
yes, serial communication to the typically the USB chip, like the CH340G or the SI2102 or the AT16, or if it's an Atmega 32U, it communicates directly to the USB and can simulate a USB device. So what that does is basically says you kind of don't want to use those pins because they're used by your IDE. And if you start wiring stuff to these things and it interferes with communication, you're not going to be able to upload and download stuff from your Arduino. You'll be stuck. So you kind of leave those pins alone normally. And here's more stuff about pin mapping. Here it says int 0 and int 1. These are for interrupts. Map to pins 3 and 4. Oh. Here's 3 and here's 4. Well, 4 is int 0, but 3, it doesn't look like int 0 to me. Question 21. What do you think? Is that true or false? Well, where's int 0 and int 1?
That'd be at 4 and 5, so it'd be 4.
Yeah, that's false for sure. For sure. I'm giving you like the whole thing, and it's up to you guys to like look at this and say, no. Int 0 and int 1, that's 4 and 5. I can't, and on the Arduino board, right? It's mapped to those pins which are labeled on the silk screen 2 and 3. So 2 and 3 correspond to PD2 and PD3, which happen to have pin 4 and 5 for the Atmega chip that they're showing here. But this Atmega chip could be replaced by something in a quad flat pack. And all the pin names, will remain the same. And the logical pin assignments will be the same, but the actual pin numbers will change. So you can't use the pin numbers. That's the deal. Because what happens when you look at the Atmega 32, 328P versus the 32U, these are different chips, right? So if you looked at, for example, 328P, which is what you've got in your Arduino Uno, right? You got a pin out. There's your 328P. And that's what we've been looking at right there on the right. Now do it again, only this time with a difference. Look at the 32U pin out. And now we see sort of like a different shaped chip, and it doesn't quite match what I had in mind. I was hoping they would give me a picture. So I guess I have to type in Atmega. There we go. So what happened, right? This doesn't, these two things are not the same, right? Look, this is pin 44. There's all these extra pins here. And now look at this. Well, he goes to pin 40 only, right? And his, he's saying something like, well, pin 12 is a crystal. And over here, I know there's going to be a crystal somewhere, but look, it's going on to pin 7 and 8, not pins 12 and 13. So when they go to a different microelectronics packaging form factor, they are at liberty to assign the chip pins any way they want to. But logical pins like int1 going to PD3 and int0 going to PD2, those logical pins have not changed. So when you go to int0 PD2 and int1 PD3, that's the same. And if you want to map it to something that's consistent with the Arduino's Uno's I'll call them mezzanine connectors, right? The shield pins. Well, then you're going to end up somewhere along the lines of the same place where these guys are going. So in other words, you want to be able to plug a shield into there and have it find the right pins without having to rewire everything. So they can standardize on the logical pin assignments for the logical pin functions, but they don't necessarily want to standardize on the pinout for a dual inline package, because that's the kind of thing that needs a socket. And people who want to manufacture in large quantities use surface mount. They don't want to use a socket. So, you know, the Atmega folks will try and do something that's relatively pin compatible by coming out with a Leonardo versus an Arduino Uno. So I don't know if you've seen these two things, in case you haven't, but the Leonardo pinout pretty much matches the Arduino pinout in almost every respect, I think. Yeah, I wish I could make this a little bit larger. I don't know why it doesn't get larger. That should be bigger. Well, let's close this. See if I can't make this part bigger. Oh, he's not making it bigger, but this is just looking blurry to me, oddly enough. A lousy picture. They should definitely give you a better picture, but these pinouts are going to match roughly the Arduino Uno. Let's see if we can get this to get smaller so I can get some of it on there. There. So here's Arduino Leonardo, and you can see A0 through A5. You can see transmit and receive. You can see all the same MISO, MOSI, serial clock, and chip select pins that we're used to. And so that sort of thing matches what we would expect for the Arduino. In the cases of much more powerful boards, they still try and match the pinout. So you could do this with a DUE, which is like a 32-bit ARM RISC machine. But when you look at the DUE, what you see is something that kind of looks like the Arduino with a difference, but guess what? It's A0 through A6. And these pins, you know, you can plug a shield into the front part and not mess with the back part at all, but they gave you an extra DAC, they gave you more A to D converters, they give you direct access to the data bus so you can expand and add RAM if you feel you need to add RAM. But look at the price. I mean, he wants $40. This thing is listing at the cost of a Raspberry Pi, but it's a 32-bit embedded controller with an ARM processor in it and doing all kinds of interesting things. So far more robust in terms of its I/O with the pins and the A to D converter and the DACs than a Pi is. And there's no operating system. So that's both good and bad depending on how you look at it, I suppose. So let's see, got some more SPI questions. Let's see what else we got here. Strain gauges. Cyanoacrylate, what's that? Somebody knows what that, oh, it says right there, super glue. We knew that. Let's see, cathode, anode. Let's see, the short leg is called the anode. These are a couple of button cells, which are being squeezed. We squeeze the two leads around the button cells, And then we can light up the LED. So if you have a couple of extra button cells, you can make a little flashlight out of it. And there's no current limiting resistor here because the amount of current that the button cells can supply is quite limited. These are like watch batteries. Your LED won't last long that way. But it might be good for the end of a keychain where you only need it once in a while. I think we talked a little bit about Nyquist's theorem, so you guys are probably well on your way to understanding that stuff. But you'll stop me if I hit on something you want to talk about. PIR sensors, I think we've talked about that enough. Permanent magnet rotors. How about signal to noise ratio? Guys, need a review of that, or we've seen that before, I think. So maybe this is a simple test. I should probably make it longer, right? So then here's an interesting thing we didn't cover. F will take literal strings and store them in flash memory instead of in RAM. And that's kind of cool, actually, because then you can have an address to the string, which can then be, let's say, referenced by other things. So if you've got a message that you want to put out regularly and you don't want to have to repeat it in RAM and take up space, you can throw it in flash and it'll just remain there. That's cool.
So that would be different than serial.print lowercase f and then the parentheses.
Lowercase f. Is that a legit usage of
Like I'm talking about the command serial.printf. Like
this is not printf. This is print with an f embedded. Whereas if you could have print line, and then there is a printf. Printf is used as a way to format with C-like formatting. So you can use printf in. We haven't done this, I don't think. I mean, not even as an example once, but you can use printf in Arduino. I don't normally do this, so I've got to Google it. There you go. Printf. So now here it says that whatever's in here, %D, that's going to be the time right in through here. And that'll get substituted in. But it doesn't look like this person got it to work. So there is a subroutine library that will support some sort of printf. So normally what you do in C or C++ is you include standard io.h or ios.h. And if you do that, you'll gain access to the printf, but you don't normally have access to that on the Arduino unless there's a printf subroutine library that you include. And then you can do it. You can do what you want. So this is typical C code, right? He's taking the buffer, he's printing it out, and he's formatting some stuff. But the question of how you can get the Arduino to do it, right? Because look what he wants. He wants to do standard IO, include standard IO.h. And then I guess he's coming up with an implementation of his own. So yeah, you can do that. I guess somebody else has already implemented something of a printf. Probably if I brought up my little Arduino IDE, we could find it in the library. I'll bet it's a publicly distributed thing. I never use it. Let's see. Printf. Yeah. That's a standard template library. He's got a micro C library plus. So it looks like plus C++ functions, including cin and cout, printf, and scanf. So that's cool. So if you want to simulate real C++, you could import this, get some examples, and then you would have a, looks like there's more than one. I wonder if they're all incompatible. I don't know which ones are good. I'd have to explore it a little bit. So, yep, looks like there's a, there is a way to do printf, but it's not a standard library. You got to install it. And then I don't know if they give you good examples or not. But I imagine they do. Examples. Printf. Is this something you guys have tried before? I don't really do printf. Where is it? I'm not seeing serial.printf. It's probably in here somewhere. Well, if we installed it, I don't know where it went. So there. How's that? Maybe they don't give you examples. Maybe they just assume you know how to do it. Oh, there it is. Maybe. No, that's a real-time compatible library. That's not right. I don't know. I don't know where it went. Maybe it's one of those libraries that you can include. So that would be printf, right? Elemental P. No, it's not there. I am not seeing it. So maybe it's here, but I got too many libraries. I'll let you guys answer that one. I don't normally play around with printf. But this will store the literal directly in Flash, which is totally different. And I think we recognize this guy. He's a Bell Labs employee, or he was anyways. And he did Darlington Junction transistors. Let's see. Here's the alternative design to the analog to digital converter. Before we were doing a successive approximation A to D converter. Here is a far more precise but far slower A to D converter, which is designed to measure something that is not changing quickly, like the resistance in a Wheatstone bridge. And that's used to drive your load cell. So that this is the heart of the load cell, giving you all of these dynamic, all this dynamic range. And what is 2 to the 24? Does anybody know? You guys don't know these things? 2 to the 20, you know that one? That's like 1 million. So 2 to the 24 is like 16 million. And that's how many quantization levels you'll have when you're dealing with the A to D converter. And if you take 6 and multiply by 24 and then add 3 dB, you get 147 dB of signal to noise ratio. That's a lot of signal to noise ratio. That, you know where that is that's right on the noise floor. So the noise floor, that's the actual noise that you get from, well, thermal noise, right? And you get the thermal noise by using the ambient temperature, and you multiply by Boltzmann's constant, and then you multiply by the bandwidth of the thing you're trying to measure. And this has an extraordinarily low bandwidth. And so that essentially gives you the total amount of noise you get from the vibration of the molecules in the conductors. So that's thermal noise. Anyways, I guess we talked a little bit about bootloaders. And Arduino Unos have a certain amount of program memory. And then they allocate some of that to the bootloader. when you get the chips, you don't get a bootloader. If you just buy raw chips, there's no bootloader. You've got to install the bootloader to get these things to work. So when you're manufacturing and you're just assembling the chips and there's no bootloader installed, you've got to put the bootloader in there somehow, or else your users will have to do it, your end users. Kilobyte of double EEPROM in an Arduino Uno. Is that true or false? You guys tell me.
Is that true?
Yes, it is. That is true. That's all the double EEPROM you get. So timer 2, is that an 8-bit timer? It looks just like timer 0 and it's used by the tone function. You can use it, but only if you don't plan to use the tone function. The tone function. What's up with that? So to make a tone using the standard tone library, they're doing pulse width modulation, right? They're changing the frequency of an output, but they got to use a timer to do it. And the timer they're using is timer 2. So if you decide you want to use timer 2, the tone function stops working. It is what you call, I don't know, is it a conflict? Oh, contention. That's a contention for a resource. The number of different hardware timers built into the chip is limited. I think there's like 3 of them. And one of them is a 16-bit timer. I think that's timer 1. So then we talked a little bit about stepper motors and half stepping. I think you guys have seen this before. And if you treat it like a finite state machine, you can figure out whether or not you could implement it with like hardware. So just like we had a hardware implementation of the pulse width modulation for the servo using the 555 timer, you kind of can do a similar sort of thing, a hardware implementation. You're not using a 555 timer, but using a hardware implementation to get the stepper motor to work. And so basically, all you really need is a finite state machine and a clock. And you can get your stepper motor to do full steps or half steps. As a matter of fact, even if you didn't want to use the clock of a 555 timer, you could still build the hardware to drive the finite state machine that comes out of here, and maybe just pulse it, advance it with a pulse from your computer. And you might like to do that if you were just going to use the serial port. You could toggle the data transmit ready line on and off, and that could advance the stepper motor. I've done that before myself, just because I didn't want to involve a microcontroller. Although thinking out loud, you're probably better off using a microcontroller at the end, because then you can add more stepper motors. So what's that Prescaler for anyways? Here's a Prescaler. I think my dentist has this. What do I do with a Prescaler? Doesn't that remove the tartar from your teeth or something? The Prescaler? Well, you know that you've got a successive approximation A to D converter in your Arduino. And so what that's doing is it's having a counter drive a DAC. And when the DAC is too low, it has the counter count up. When the DAC is too high, it has the counter count down. And that's fine. That works great. But the counter only counts so fast, and the clock runs at 16 megahertz. And you kind of can't respond that quick. So in comes the Prescaler, and that reduces the sample rate for the clock. Reduces the rate at which you do an A to D conversion. And you can change that frequency. That's what the Prescaler is about. And then there's this this image here. I don't know why this doesn't come up as an image, and I can't seem to select it either. Gee, that's weird. Isn't that weird? Why can't I select that? I don't know. Well, anyways, if I could select it, I'd take a look at this thing, but for some reason it's not letting me. Maybe that's my browser. So this is set the bit, that's clear the bit and clear the bit. Let's see now. Yeah, here all three things are being set. I'm a little annoyed that I can't open up this picture. Anybody know what could be wrong here? How come I can't open this picture? I don't know. Can you guys open it from your end? Are you able to see this? Maybe if I...
No, we can't see it.
You can't see it, and you can't open it, and you can't select it.
It's just like a little blue square with a question mark in it.
All right, so this is question 36. Let me go off screen and see if I can get into this.
It could be the format or the size of the picture.
I don't know. It looks like something is wrong. Let me see if I can open this up. No, he's not letting me in either. Shoot. So what do I got to do here? Close it. I hate this nonsense. I'm having a stupid Blackboard day. What if I just type it in? There, that wasn't too painful, was it? What could possibly go wrong? Ah! Screw this. Man, this pisses me off. Can't I just get a picture? I just want a picture. And hit images. There they are. That's what I wanted. A picture. Copy the image. Okay. Take the image. Put it over in here. Formatting. Submit update attempts. You guys have already done 3 attempts? You're a bunch of wild men. Wow. How do you do this so fast? You did 100 questions in 3 attempts already? That's ridiculous. You're not taking this seriously. Let me see if I can recover this. Question 36. Leave page. Oh man, he's going to make me start again. This is fun. I like Blackboard. I really do. I like it because it teaches you patience. I'm learning patience. Begin. So we were on question 36. Yay, we've got a picture. Hurrah. Hurrah. Boy, that's fun. Well, I'm glad we got that squared away. So let's see what else we got here. More screwy things. Sorry about the blemish there, especially the part where I had to like sit here and edit it. Probably next time what I'll do is I'll just make a note and say something like, oh, I don't know. I'll fix it later, offline. Fix it offline. Fix it in post. Consider the following code. According to the reference manual, the bits for the 80 mux look like this. And here's the reference manual. This is the data sheet. And now you have to decide which of these things is correct. So here it is 001, right? Does that correspond to internal reference 2.56 volts? ADC channel 0? Hmm. 001, I guess that would be this one. That's external reference, right? So that can't be right. Here's 110. Look it up. Internal reference without external bypass capacitor disconnected from PV0. This is internal reference 1.1 volts. So that's not right. Here's 101. Let's look at that. 101, that's external voltage reference. This is external voltage reference. PB0 ADC channel 0. That doesn't seem right. Now here's 001. 001. External reference at PB0 A ref. Internal voltage reference turned off. And there you go. So there's your sign right in through there. So this is designed to make you look these things up, read the directions. This is how real engineers work, right? You have to read the data sheets. Typically every chip, unless it's from Apple, it has a data sheet. Any chip that's manufactured so that people outside of the company can use it will have a data sheet, because people can't use a chip unless it has a data sheet. In the case of Apple, they'll have a data sheet, but they just don't share it with you because they want to keep it company proprietary, and they don't want anybody making Apple clones out of their M1 CPU or something, right? They consider that a competitive advantage. Got their own CPU. Nobody else can have it. It's an Apple CPU. Locks everybody else out. Nice and closed. They don't believe in open source. It's not part of that thing. So then let's look at this question 38. How are we doing on time? Good. Consider the following Atmel documentation. This is another read the manual kind of thing. Here's the analog to digital converter status register A. And here's status register B for what it's worth. And what was the question? Consider the following images. With 80 mux equal to binary 0, 1, 1. So 0 would be RFS 1, would be a 0. RFS 0 would be a 1. So that's 0, 1, and then 1, 80 LAR. So that's 0, 0, 1. Sorry, 0, 1, 1. So 80 LAR is asserted as 1. So we know that it's got to be the first one or the third one. And so now we have to know, is it the most significant byte coming first or the most significant byte coming last? And that's what you need to know. 80 LAR. So you could look it up, I guess. The C compiler does no checking to see if an array access is within legal bounds of the array size that you have declared. This is in comparison to, let's say, the Java compiler. And so that That's true. That's true. C compilers don't care if you go off the end of the array. They just crash the computer for you at runtime. Hard, crash it hard. So let's see now. Closing S2 and S4 are the only way to hit the brakes. And what does that do? Well, it creates a back EMF that shorts out the motor and basically makes it harder to turn this motor. Well, you could also close S1 and S3 and leave S2 and S4 open, but you'd never close S1 and S2 at the same time because that would make a short circuit. So basically shorting out the motor's legs is a way to hit the brakes, and you can do that with either S1, S3 or S2, S4. Am I going too fast for people? Question 41 looks like it's got a little bit of a blemish in the spelling. There's a typo. It says number. Now there's 4 attempts. I just updated this, question 41. I updated it off screen so that it would not have that blemish in it. So let's see, what do we got here? CBI stands for clear bit. SPI stands for set bit. There's a register called the SFR, and we're going to clear one of the bits in the SFR. SPI will set the bit number indicated by the bit in the register's SFR. So then CBI clears bit 1 in the SFR. Oh wait, CBI must set bit 1. Set bit 1. Does it do that? Does CBI set bit 1? I said clear, but look at what it says here. It says set. So that can't be true. That has to be false because the whole point of S is to set and the point of C is to clear. Wow. All right, you guys, you help me. What's the answer to this? True or false? A BJT, bipolar junction transistor, a current control current source, is hooked up staggered to like this. And I want to make one large control current called the Darlington pair or Darlington transistor, and that controls a much larger current. Is that true or false? You can't sit like lumps on bumps. I'm going to call on people. August, what do you think? True or false? Bueller.
That would be true, Professor.
Yes, that is correct. Thank you. And then let's see, what do we got here? The following code in DAC.H shows that chip select is on pin 9. Well, I guess that's too obvious to go over. That's just true. And then following configuration enables only simplex communication. Simplex communication means only one direction, right? So is it only one directional communication?
This be false because there's an arrow going back into the master.
Exactly right. That's exactly right. So that's full duplex. Let's see. Oh, look, here's another Hbridge. An Hbridge can be used to reverse the current through a motor. Close S1 and S2 And the motor will run backwards, S1 and S2. Does that sound right?
I think it's false.
Yeah, that's false. That'll short out the power supply, and sparks will go flying, and pieces of the motor will incommodate the passersby, and it'll just be a mess. Who won't like that? Let's see. Question 6. In the following code, we need some header files in the same IDE in order for the IDE to compile. Sounds like they have to be in the IDE. The IDE. Any ideas on this one? Looks like somebody wants to use the A to D converter and a DAC, and they wanted to find these header files. Well, I mean, here we go, right? Somebody said, I want to include DTMF.h. You look at DTMF, and he wants to include DAC.h, and you go over here and you find DAC.h, it's here. So we need to include the header files in the same IDE in order for the IDE to compile. That sounds right.
Wouldn't that be false though, since it's saying in order?
In order to, in order for. They don't have to be in, oh, I see what you're saying. To effect compilation, I should say, I suppose. They don't have to be in order, that is in one order or another order. I guess that's got a dual meaning. I hadn't thought of that before. It is there to enable. In order means to enable in this case, the compilation. In other words, if this wasn't there, it wouldn't compile. Put it that way.
So you could have the include ADC.h before the DAC.h. So it doesn't matter what order as long as it's like the first thing in the code, right?
Yeah, I think that's right. In order meant to enable, not that it had to be done in a specific order. I suppose question 46 looks ambiguous as a result. Let me reword that. So I'm just going to make a note offline, and I will do that. Question 46 reword. And we're going to change in order to enable. It's my casual way of speaking. So the same IDE to enable compilation. That would have been the proper way to say that. Let's see now. This defines a pointer to an integer type variable. Does that sound right? What do you think? Does that look like a pointer? And what's the value of what's inside of this my PTR? What is the pointer? Shamrock. Is this a pointer?
I believe it is.
Yes, it is.
True.
That is correct. It's a pointer to something of type integer, and if you're on a 32-bit machine, this is a 4-byte quantity. So it's an address. So now here's an interesting question. Question 48. Let's see now. This is a timing register, time control register. Let's see. It's got overflow interruption. Looks like you can set specific bits in the time control register, TOIE 0. Is that in here somewhere? Yep, there it is, bit 0. And then here we are taking TOIE 0 and setting it equal to 1. So that's going to set the timer register, enabling overflow interrupt. Interrupt enable. Overflow interrupt enable, OIE, for timer 0. And here's an output control register. And timer control. Let's see what we got here. Timer output interrupt enable for timer number 1. Let's see. Timer at Tim SK1 controls what's generating interrupts. ICIE, input capture interrupt enable. OCIE, output compare, match interrupt enable. TOIE, timer overflow interrupt enable when counter wraps. So basic idea is you'll have a prescaler. It'll choose how fast your counters are counting. You'll have a timer and that'll act as the register. And when it overflows, it creates an interrupt and that causes you to have to service the interrupt and do whatever you have to do at whatever rate it is you're doing it. So if you're sampling at 25 microsecond intervals, then in principle, you'll have a timer that triggers every 25 microseconds, and then you'll proceed to go and sample the A to D converter and take the input and run it to the output. So now here's a question. What does set bit timer output interrupt enable 1 do? It says here, enable an interrupt service routine invocation whenever the timer reaches. Whenever the timer reaches. Is it missing? Reaches, it should say reaches. Reaches its compare. Shoot, there's another bug in this question. Bugs in the question. This is what happens when you have 100 questions. So there's a bug in question 48A. It should say whenever it reaches the end of the register, whenever it overflows, reaches 0, enables an interrupt frequency at some in hertz, which will be equal to the clock speed divided by the prescaler times the compare match register plus 1. So that's going to cause the overflow. And yeah, it does that too. So it enables an interrupt frequency that is a function of the compare match register. Compare match register looks very similar to this. So if you want to interrupt every second, compare match register 16 million divided by prescaler times 1 minus 1. With a prescaler of 1024, you get 15,624. Since 2 at the 6 is less than 15,624, which is less than 65,536, you must use timer 1 for this interrupt. Timer 1's a 16-bit timer. You can't use an 8-bit timer if you want to count up to numbers like this. This is one of the reasons why people use prescalers, folks. If you want to use an 8-bit timer, you've got to slow down the clock that you're using to count, or else you're going to overflow before you get to the number that you're wanting to count up to. And then the answer to that one is going to be all of the above, I think. But this was complicated, at least in part because the compare register was missing. So I got to put the compare register in there. I made a note. Let's see, is it true you can never mask an interrupt? T Young, Kim, are you there?
Yeah.
Yeah, is this true or false, do you think? Question 49.
Is that false?
Yes, that is false. You can mask an interrupt. It's particularly important for you to do it if you're servicing an interrupt So in the middle of servicing an interrupt or in the middle of doing some timer specific stuff like setting up the timers, it's good to mask the interrupt. It's actually something you'll want to do. So if you looked at, for example, the DTMF code, you'll see a little bit of timer work in here somewhere. I think, yeah, here I call no interrupts. And then if you wanted to find the no interrupts subroutine, that would be in here somewhere. I hope. Or not. Let's just look for it. Oh, I guess I don't need the code for that in here. For some reason, I thought the code was in there, but it's not. I guess it's just built in. So that's cool. That masks the interrupts. If you want more than 500 milliamps from a ULN 2003, stacking one chip on top of another should get me it. Get me it. This can't expect decent English from engineers. It should get me it. Well, I'm going to reword that. I mean, it's not wrong, but well, the English isn't good. It should enable, it should say. So stacking, yes, stacking will get you more current. And they all have the same pinout. So it's essentially like having 4 transistors because each one is representing 1 Darlington transistor. And each one actually has 8 Darlingtons. So you can just stack them. And we use these for the stepper motor. So the ULN 2003 was actually part of the stepper motor lab that we did. So that was good. How am I doing on time? I got a couple of 5 minutes. Good. Only pins 2 and 3 enable interrupts in hardware as shown here. We see a button for pin 2. I'm missing a picture again. Geez, you know, I went over this thing and I missed, I need quality control. Missing picture. Somehow the pictures aren't sticking. I don't know why. We'll fix that.
Question 78 also has a missing picture.
Let me zip. All right, so we're on 51. Let me zip over to question 78. I fixed the pictures in here this morning. Those are working. Question 73. Question 78 is, oh crap. All right, I'll fix that one too. This is what happens when you have 100 questions. You're bound to have problems. I'll fix. Don't worry. Let's get back to question 51. Unless you guys are wanting to put it off for a little bit, maybe take a chance at, why don't you take a stab at looking at this thing over the weekend and come in with your questions on Monday. I think that's a way to go because it's too much. Right? We already did over half the test by going through the 51 questions, and there's diminishing educational returns to keep going. So what we'll do, unless you guys see any other blemishes, and if you do, shoot me an email, even if you're offline when you're going through it, and take note of the questions you want to ask, and I'll try and address them on Monday. So that ought to get you guys going. And if you've missed yesterday's lab, I've recorded it. It's up on the web. Not to put too fine a point on it because I did this once already today, but I'll do it one more time. If you look at the microprocessors list and go to the bottom where the, there it is. Nope. There it is. Lab review. So that's in there. And I don't know if you've seen this, but this is worth looking at. So I'm just going to, show you my little Bluetooth demo. I don't think I showed that to you before, but this is still sitting here on my desk, although I've pre-recorded this one here. Let me take a look at this. So that's a Pro Micro. This is a an HC05 Bluetooth module, and they're on the same sort of range as my little Mac. So my Mac's got Bluetooth built in, and I can communicate to the Mac directly using this little what do they call that, a micro strip antenna. And so this is what they call the circuit IO block diagram, but it's actually a schematic, I guess, of how you can lay it out on the breadboard. It's kind of more clear when you look at it here. And the nice advantage of the circuit IO is that it not only gives you the way to wire the breadboard, but it also gives you a sample code. And sample code's really nice. And so then you can kind of test everything to make sure it all works before you make it part of your own project. And a lot of times what people do is they'll get like a sensor and a little app on some sort of an Android or iOS phone, and then they use the Bluetooth to communicate to these mobile devices, and that enables you to take your app and do things like visualize the pulse or visualize sort of like the amount of alcohol that's on your breath, or do the kinds of things that are kind of useful as part of, I don't know, computer enabled things, measure blood sugar, whatever it is you like to do. Here I'm swapping an Arduino Nano for the Micro, and you can see how quickly it does the wiring. It's practically instantaneous. So that's pretty slick. And there's the code that he gives you, and that'll just work. And that's really valuable too, because that'll just cut out the whole part about where you have to like read and understand the manual and figure out whether it's a hardware problem or a software problem. And then I use the HC05 as essentially a virtual serial port. And so I can send messages to the serial port and receive messages from the serial port. So I need two serial ports, one for the HC05, which is established under Bluetooth, and the other for the Arduino. And then I built a little chat program so I can type in on the left, and whatever I type in on the left should come out on the right. And similarly, whatever I type in on the right should come out on the left. And so you can see here, it says, this is the Arduino monitor. So I typed into the monitor, came out on the HC05. And then I can go into the HC05 and I can type some junk. And presumably, there it is, coming out in real time as I type one character at a time. So it's demonstrating a chat program using Bluetooth. Bluetooth is kind of limited. It does what it does. It's a serial port. But there is an alternative Bluetooth protocol called HID, and it will simulate a keyboard and a mouse. And there's also an audio Bluetooth protocol. In fact, there's so many different ways people have reused Bluetooth. They've gotten to Bluetooth 4.0, which introduced mesh networking. And then they got Bluetooth 4.1 and Bluetooth 5.0 now, which has IP version 6 in it. So you can actually do internet protocol, and then you can do packet forwarding and have an actual IP address on the Bluetooth modules. So that's kind of cool. I mean, Bluetooth is being reused in so many different ways. So that's what I got for you for today. And I thank you for your attention. Let me stop this video here. And
Professor, one question.
yes.
Viz Lab, do we have to submit anything for it? The one you just went over?
The one from yesterday? No. No, you've got a final
Okay.
project that's due in a week. And the only thing I did yesterday was I went over that final project so that if there were any remaining questions, you could try and get them addressed. So this is in the nature of the DTMF review. And so that's what I did. I just went over any questions that were remaining. It was not a well-attended session, but that's okay. I don't mind. I recorded it so that people could see it. They want to watch it later. So,
Okay, thank you so much.
sure thing. All right. Well, have a good day and stay safe.
Professor.
Yes, sir.
So are we meeting during the lab time next week? Or
If there's anything left over in terms of questions that you might have, I will be there at 10. If nobody else shows up at 10 and nobody has any remaining questions, that's fine. I don't need to, chit chat, but I'll be there for any extra help that you might need. I'll come in at 10 on Zoom for anyone who needs extra help with this DTMF final project.
all right.
Awesome. Thank you, Professor.
Thank you. Thank
Have a
you.
good one.
You too.
Professor,
Yes, sir.
I'm having the same problem that Shamrock is having with the Blackboard since they switched it to the graduate level. So I emailed Marcy. I just wanted to let you know.
Oh, wow. I'm sorry about that. Yes. I'm glad you told her.
Okay.
And I'll let Mary Kleps know about it as well.
All right, great. Thank you very much. I just wanted to let you know just in case there was any discrepancies with the homework because I'm not able to see it now.
You can't see the homework?
No, it's Blackboard is basically blank for me. I can see the class and I can click on it, but there's no population in any of the tabs.
All right. I'll let Mary Kleps know.
All right, great. Thank you very much.
Thank you. Bye-bye.
All right.